And in this lecture here, let's now study how we can find derivative of logarithm functions. So in my style of teaching, actually, let me put it this way. There are many other professors teaching finding derivative of logarithm function as a separate independent topic. But for me, in my own experience teaching, I find that it's best to teach how to find derivative and how to derive the derivative of a logarithm function after we've learned about, my students learn about how to find derivative of an exponential function. So this lecture specifically, any viewers currently watching this, I highly recommend that you watch my lecture on how to find derivative of exponential function, and then we're going to go ahead and continue here. And then as well as outside of that, I also feel it's best to deliver this lecture here about taking derivative of log function after my students learned about implicit differentiation. And so my bottom line now is that before we can proceed further into this video lecture, I highly recommend that if you haven't seen my other lecture on how to take the implicit differentiation, go ahead and give it a view, and then and also view my lecture on how to find the derivative of exponential function. Then once you have viewed those two particular lectures, then now we can go ahead and proceed into this video. Okay, but now other than that, here we are at being able to find, let's now learn how to find derivative of a logarithm function. So the logarithms. So now for the logarithms function, and allow me not to go too far back of reminding you what a logarithm is, because that was what pre-calculus course is for. So here logarithm is simply at this point here we understand that logarithm is a function. So we can have a log base 2 of x, that is a function. Okay, we can have a function being a log base 10 of x. Okay, and then but then as a worldwide convention, then anytime it comes to log base 10, then we can write just simply the log symbol and skip the base right here. So these are the bases of your log. And as I said, if you're not sure what I'm talking about with logarithms, I highly recommend that you review your skill in understanding what logarithm is all about, because here I'm only going to take the next step, assuming that you already understood you already well understood what a logarithm function is. So these are called the bases, and when it comes to the log base 10 right here, we are skipping the base. We can just simply write log, and mathematicians, people worldwide who study math will understand that this is log base 10. And then another special log right here. So basically anytime we're having a positive number, we can treat that as a base, and your pre-calculus teacher should have mentioned that as well. Anytime we have a positive number, we can create a logarithm out of that base right here. And so the number e that we've learned in some of my earlier lecture, in some of my other lecture right here, the number e is approximately 2.718. Gosh, such a ugly looking constant, just like the pi right here, approximately 3.14 and so on. But even though being not so nice looking, but it's a positive value, so we can use that as a just fine to be the base of a logarithm. And so we define log base e of x here as a short symbol, natural log, ln, as a way to pronounce it, to verbalize it, it's a natural log, ln. So log base e, another way of writing that, ln of x, or the natural log of x. Okay, so these are just some brief, and so generally speaking, outside of the two special bases, base 10 and base e right here, then generally anytime we're looking at logarithm function, then it's log base a of an input argument. That's logarithm base a. Okay, and a here, the base a here must be a positive number, a positive constant. Okay, And so now, before I go on further, just one more brief review, and I promise that's about all the review I need to remind anyone viewing my video. And I'm pretty sure you have seen this as well when you were formally learning your pre-calculus courses. But when we have, what it means being a logarithm is that when we take log base, say for example, if y equals log base a of a number x, so x here is being the input, and for now at our calculus level, we call that this is a function logarithm base a of x. But think about the way how we operate. Then log base a of x to equal this value means the base a. So formally speaking, for calculus students, this equation, this equality is true if and only if, or another way of saying, verbally speaking, it means, so we're saying a number log base a of x equals y means the base a being raised to power y equals x. Okay, so like I said, I only go brief here with this because allow me to assume that you have seen this back in your pre-calculus course, but you do need to nail this understanding regarding logarithm. You need to nail this down before we can advance to the next step and finding and learning about the derivative of these logarithms. Okay, and that's about all it takes right there. That's about all it is. So now, among all the general logarithms, among all the logarithm functions generally regarded by log base a of x, it's just the number e is so special, even though it's not a nice looking number, but log base e will be the one primarily focused as our main target here throughout the entire discussion in this topic. And then from there, we're going to create an extended version for all the general logs later, afterwards. Okay, so now my plan here is we're going to start out studying the logarithms, the derivative of natural log base e of x. So now we're given the function y equals natural log of x. It's a logarithm. It means log base e. Okay, it means a log base e, and we need to find, our goal here is to find dy dx. Our goal is to find the derivative of this given function, dy dx. And so, in that way, the reason I had to briefly remind anyone viewing my video here about the meaning of logarithm, because, and I said earlier as well that it's me, when I teach this material, finding the derivative of logarithms, I find it's best, and I have been believing it, that it's best to deliver this material after my students have learned about implicit differentiation as well as how to find the derivative on exponential functions. So those are the two lectures that you need to see before we arrive here. So now, to find this derivative, yes, I do agree that we have a completely brand new function again. We have never had any quick rule for that, and as a matter of fact, we are at that stage right now. We're trying to find a general rule for finding derivative of natural log of x. So ideally or theoretically, we have to stay with the limits definition. We have to stay with the limit definition, but as I said, I find it not too fascinating going that route after a couple of years of teaching in calculus, so I decided to go this way, and it's been successful. And then when my student gained more majority, then I was able to show the actually more original method. But so now let's to derive the derivative here for natural log of x. Let's go this way right here. How about first, I'm going to start out, this is the algebra for now. If y equals natural log of x, recall for yourself, natural log of x is log base e of x, log base e of x. Then that means, formally speaking, we're writing that y equals natural log of x if and only if. It means it's base e. Natural log is base e. So e to the y power or the y exponents must equal x. Okay? E to the y power must equal x. And so now, once we arrive at this point right here, now the advantage of doing this now is that what I did here is that I bring my equation from the form of explicitly defined y as a function of x. But now I have rewritten that equation in terms of as a function e to the y equals x. So this equation here, I see that as an equation, and now the y variable now is kind of still, it's the function of x, but it's now implicit. Okay, because it's e to the y and then equals x. So it's kind of implicit. So now I start using that term implicit because you start seeing where I'm going. Now from this equation, I'm going to use that technique of implicit differentiation that viewers at this point, as I recommended earlier, go back, search for my lecture on implicit differentiation, understand that skill, and we apply that here. So using implicit differentiation, this is what I'm doing. If e to the y equals x as an equality, then we can, and remind yourself, this symbol here is intending that y is the function. Y is a function of x. And so now I'm going to take the derivative of this function, but in terms of x. Okay? And so I'm going to do the same thing, take the derivative on the right-hand side of that equation in terms of x. And since it's an equality originally, and so taking the derivative on both sides would also give us equal derivatives. Okay, and so this is the step where I'm at right now. So I'm taking the derivative equally on both sides. So, and if you have seen how I have done the implicit differentiation in the lecture specifically on implicit differentiation, then this side here would be easier to handle first of all, because this term itself is already explicitly defined my term in terms of x. My function here is already explicitly defined as a function in terms of x, which matches with that variable we're intending for. So the derivative of this term is simply just 1. Okay? And now, this term here, it's time to move on to the next step right here. So on my left-hand side, it's e to the y, e to the y. Let me bring everybody to my other board. It's e to the y. Okay? And we want to find the derivative of this e to the y in terms of x. But no, recall yourself again. Y is a function of x. Y is a function of x. That means this is only an outside function. E to the y is an outside function. This is outside function. Okay? And the inside function, what is the inside? Just some function, just some unknown function of y. Pretend that we're going completely implicit right now. Then, okay, some function of x, right, being in y. That's all I can say. That's all we need to know. And so in that way, this derivative here is going to be, on scratch work that I'm doing here, see, the derivative, we just now learned about derivative, how to find derivative of e to the x. So same here, the derivative of the outside, according to chain rule, the derivative of the outside is e to the y. Okay? And we got that from learning the derivative formula for the exponential function. But now I need to multiply with the derivative of the inside function. The inside is just some function of x, and pretend that we don't know what that is. So here I'm doing multiply with dy dx. We have to multiply with that. So chain rule says take the derivative of the outside function and now multiply with the derivative of the inside function, where it's just that implicit derivative right there. Okay? And so now I'm going to put all that here back into my other board. So this term on the left-hand side produces e to the y times dy dx. Okay? and victory is right around the corner. So now e to the y in product with dy dx. Everything here came out from my explanation earlier in the other board right there. And it came out as a consequence of using the chain rule. So now it's implicit differentiation technique again. What we need to do now is just simply solve for dy dx specifically. And to make it explicit right there. So now that means dy dx can be found by simply dividing both sides of this current equation here by e to the y. So now that means I'm going to produce a 1 over e to the y. Okay, in my derivative. So dy dx is 1 over e to the y. But now in this case, so normally if this was an implicit differentiation problem, then we would be fine just here. But now I want to go one step further. It's right here. What's e to the y? E to the y is equal to x. Okay, e to the y equals x. So that means your final derivative, dy dx here equals, dy dx equals 1 over x. That is a huge bingo. We have found the derivative for the natural log function. All right, so let's now put on a final conclusion here. I'm going to take a moment erasing my board here. All right, so what have we learned here? If our function, okay, formally speaking, f of x equals natural log of x, okay, then in that case, then in that way, our f prime here is simply going to be 1 over x. Okay, we made that discovery. All right, so short way of writing this rule, see, the derivative of natural log function. So this prime symbol here is kind of assume the variable here being the x right here. Whatever the variable, the only variable being written in the problem. So natural log of x, take the derivative, gives us 1 over x. That's another way of writing your rule for taking derivative of a natural log of x function. The derivative of natural log of x equals 1 over x. Okay? Or a little more formally, see, we have natural log of x, and now when we differentiate, take the derivative of that function. And so as I said, this is an alternative way of writing, but that's quite clear about what variable we are targeting at. The answer is 1 over x. 3 different ways how we can express that rule is like that. All right, so that's how we find derivative of the natural log function, the logarithm base e as a function of x. All right. And so now once we have seen that, and eventually I will get to doing some actual examples here, but let's now from this right here, but sadly natural log of x here is only the special base e, but the actual family of all logarithms is a lot more than just log base e. There's log base 2 of x, there's log base 1/2 of x, there's log base pi of x. So generally, if it's a log base a of x, what should be the general derivative? All right, so and so now let's recognize a few special ones. So I'm gonna say we're given, how about y equals log base 10 of x. Okay, and so skipping the base here means it's log base 10. And then let's find dy dx. Let's find dy dx. And now I am going to use the same approach as we have seen earlier. I am going to turn my equation here into an implicit equation where it's only implicitly defined y as a function of x. So algebraically y equals log base 10 of x. That means 10 to the y equals x. Okay, log base 10 of x equals y means the same as 10 to the y equals x. And so now picking up some the experience that we have seen in e to the x and e to the y equals x, the problem earlier, or natural log of x function earlier. And now I can do this. I can take the derivative. And here I actually meant 10 to the y. So I'm going to take the derivative in terms of x. And that should equal to the derivative in terms of x on the right hand side as well. So in my next step, of course, this is going to be the right hand side gives me, how about I'll just write it right below this. So the right hand side becomes just 1. Okay, the derivative of some function already explicitly defined in terms of x. So now power rule kicks in, and the derivative now is just power 1 multiplied down, subtract the power by 1, we're ending up with 1. This left hand side here, see, there's the outside function and the inside function. And so now allow me again to get on the other board right there, and let's do a little more scratch work. So a little bit more scratch work get me to all right, so 10 to the y. Okay, but now this symbol here is telling us that y is a function of x. So once again, with this 10 to the y here, if we're taking the derivative in terms of x right here, then that means y is an implicit function of x. Y is a function of x. And so that means we have the one we're seeing right now, 10 to the y, is only the outside function. Okay? This is the outside function. And then the inside is just whichever the x expression, right? The x expression inside of the y variable. Okay? And so now in that way, taking this derivative, we've learned from my lecture about how to find derivative of a general exponential function. Then the derivative of this outside chain rule says we have to first start out by finding the derivative of the outside. So the derivative of the outside is 10 to the y multiplied with natural log of 10. Because this is just a general base, not a base e, so derivative of the outside function is 10 to the y times natural log of 10. Okay, and we're keeping that 10 to the y right here, we're keeping that the y right here, the same variable. And now chain rule says we have to multiply with the derivative of the inside, but the inside is just some expression, some x expression inside of x. Okay, so some expression in terms of x inside of y. I meant inside of y as if I accidentally said x earlier. So now, but we don't know what that expression inside of y is. We don't know what that x expression inside of y is. And so now when we take the derivative, then we have to leave that as the implicit derivative dy dx there. And that completes our chain rule. And so now I'm going to use this and put that in my other board. So that here gives me implicitly taking the derivative. We got 10y times natural log of 10 times a dy dx to equals 1. Okay, and so now I'm ready for my next step. And so here again, ideally as the work finding the implicit differentiation, we're done, but let's solve for the dy dx. So solving for dy dx, I'm just going to divide both sides by all that 10 to the y times natural log of 10 right there. So that means we're looking at 1 over 10 to the y times natural log of 10 in all of that product in my denominator, stays in my denominator. And now again, recall for yourself, from this relationship right here, 10 to the y equals x. So right there, we can actually step one step further because we already knew what 10 to the y is. And so 10 to the y indeed equals x. So now this overall expression becomes 1 over, so all that 10 to the y now is x times natural log of 10. Okay, and so now what we have done again is that we found the derivative. We found the derivative for log base 10. So what we have found now is that log base 10 of x, taking the derivative, gives us 1 over x times natural log of 10. Okay, and then here it's just a small problem I brought up, even though I spent almost as much amount of time as did for the natural log of x, but I intended that this is only one little problem. And so I'm not going to call that an example, but in my next board right here, allow me a minute or so to erase my board. I want viewers who are following my video here to recognize on your own. So let's do a quick little FYT again. Okay, so you can try that. How about y equals log base 2 of x, log base 2 of x, and now go ahead and find for me dy dx. Okay, use that idea of turning your equation into an implicit equation and then take implicit differentiation. Okay, so go ahead and take your steps, rewind my video to learn some generality and apply the steps I've done there to this particular problem. And then let's see what your answer is. Okay, all right, so now hopefully you're back. So the dy dx I'm expecting here is going to be dy dx for this problem. It's base 2, right? The function, the final derivative is 1 over x times natural log of 2. Okay, so you got one problem done. Hopefully you completely did that on your own, not only just to keep resuming the video to wait for my answer, because I didn't show my step here. So what about one more little FYT? So how about log base 5 of x right here, and let's find dy dx. So once again, go ahead and pause the video, take out a piece of paper for scratch work, write your steps and find for me the derivative. Use the exact same idea as how you have done that in the earlier problem, and then find the derivative for log base 5 of x. All right, so now as you resume the video, I suppose you're ready for the answer. So I'm not going to show the steps. I'm only going to write down the final answer for this. But so ladies and gentlemen, the derivative here, dy dx for this function, our function was log base 5. It equals to the derivative of log base 5 of x equals to 1 over x, again, multiply with natural log of 5. All right, and so now quite a few problems. It's now enough to recognize a generality. I could have also show a general proof of this. It could also be easy, but I would save that as maybe a challenge problem somewhere here and there for my actual students here. But for general viewers here, I'm just gonna go by, we go by experiments. Okay, we're experimenting out different problems and then we recognize a generality here. Okay. All right, so now to conclude out an actual formula, an actual rule for a general logarithm, a log base, any base, doesn't have to be e. So generally, if y equals some log base a, some log base a of x, okay, not necessarily base e. And base e stay in the same rule. But for now, I just want to tackle down, the general logarithm derivative for here. So if y equals to log base a in general of x, then if that is so, then the derivative dy dx here equals what we have found here, let's put it all together. It has that similarity with the logarithm, the natural logarithm, 1 over x. But now, being a little more than the natural logarithm's derivatives, here it's 1 over x, but in the denominator there's natural log of a, the base that originally came with your logarithm. Okay, so that's the derivative of your logarithm base a right there. And so, and then again, looking back at what we have done earlier, see, if we're looking at natural log, if we're blending our rules into what we've learned here, can we treat natural log under this? Can we bring natural log, the derivative of natural log of x under this rule? Sure we can. See, think about taking this derivative and applying this general rule for general log at any base right there. Then it's 1 over x times natural log of, I'm going to bring base e in here, okay? Because it's natural log is log base e. So if we're applying this general rule for all general logarithms out there into this special natural log of x, it's going to work as well. And what's natural log of e? It's 1. That's why the final answer is 1 over x. It was 1 over x, and now it is, again, 1 over x. All right, so now for the general, a shorter version of this general logarithm formula is that when you're looking at log base a of x, okay, taking the derivative gives me 1 over x times the natural log of a. That's another way of writing your formula. Or we can also have, alternatively, we can go differentiating in respect to x. Log base a of x okay, that gives us 1 over x times natural log of a. Okay. 3 different ways how you write your rules for taking derivatives of logarithms, not only the natural log. Okay. All right, and so now we are ready for doing some examples of logarithm, taking derivatives of logarithm functions. So just like how we learned it in exponential function, the rules for taking derivative of a logarithm, any general logarithm function, is quite specific for the logarithm function. So so no instructor will be giving examples out there that hey, just find the derivative of the simple the natural log of x. So those are way too easy, and we have already derived and we've got the problem done. So now again, I have to remind anyone viewing this video that all the basic rules and the product rule, the quotient rule, plus the chain rule, those rules are all I consider as the universal rules. So now in any of these examples I'm bringing up right here, we are about to see a good combination, a good mix of all these rules being blended together in any of my example problem. So let's look at example 1 right here. All right, so we want to find the derivative of, so if the function was written in functional form, once again we use f prime, or if the function was written originally in the equation form, and we find dy dx. Okay, so find the derivative, either f prime or dy dx. So now our first function here, how about given out to be the x squared plus 4x and multiply with natural log of x. Okay, and so what I see here is that we are having a product that existing between this polynomial x squared plus 4x, and it's in product with our natural log function. And so now I pointed out and I put in a little dot in red ink right there indicating that. So now we're about to apply the product rule. So product rule says to find the derivative, we must first take the derivative of one of the factor. So the first one to come, so now I'm going to take the derivative of x squared plus 4x. Right? Take the prime of that, and we're going to multiply the derivative of the first function with the other function without derivative. So I'm going to multiply that derivative, the derivative of x squared plus 4x with natural log of x, keeping natural log of x the same. And just like that, we are now, the next part of the product rule says we're going to keep the first factor there the same, but now I'm going to multiply with the derivative of the next function, which is now its natural log of x turn to get taking the derivative. And so now that's how we lay down the product rule and getting ready for real action. And so now when the real action kicks in, f prime now will turn out to be, so the derivative of that, so simply the sum rule is here, and the little bit of power rule is here. So I have 2x plus 4, okay, plus 4, that's the derivative term by term for my x squared plus 4x. And now I'm going to multiply with natural log of x. Okay, and so that takes care of our half of our product rule. And now we're going to need to add. And so x squared plus 4x is being kept the same here. And now we're going to multiply. So just now we learned about the derivative, specifically the rule to find the derivative of a natural log function. So this standard natural log function is going to have derivative 1 over x. Okay, and so now at this point, as far as being able to find the derivative, we're done. Okay, we're done. And to be honest, for this function right here, even if you are asked to simplify, there wouldn't be much that we can simplify. So I would call this problem right here right about the end of our problem right there. It's already in its quite simplified form. Or maybe really, if you have to simplify, then you can multiply the 1 over x here for each term right there. Okay, so 1 over x being distributed for each term, but that's about it. So in that case, if you have to simplify it according to your instructor's request right there, or your instructor's requirements, then 1 over x multiplied with x squared plus 4x. And so now, but the first term here looks like there's not much we can do. So there's a 2x plus 4 in product with natural log of x. That came straight out from the first term, but then the next term here, if we combining, if we distributing that 1 over x for each term, 1 over x cancel with x squared, giving us an x plus, and now x cancel with this other x, so x plus 4. And that's about all we can do. And then this is our final answer, which is a little bit more simplified. All right, and so now that is how we have done with part A of our example. All right, so let's now look at part B of the example, example 1. So we have a function, how about y equals, and then here let's look at, let's say, log, so this is skipping the base, so log base 10 over, how about x squared plus 5 here. So what I have here before proceeding into the actual finding derivative, then we can observe that our function here is a quotient. So you see, the big thing that catches everybody's attention here is that we have a quotient. There's a numerator, there's the denominator right here, and then inside of the quotient here, the numerator is a logarithm function, log base 10, and then in the denominator here of our current quotient, then we have a polynomial. And so now in that way, to find dy dx, having a clear understanding of what our function is, it gives us a good plan of how to handle the derivative, how to find the derivative successfully. So now the quotient rule is what we need first thing in line. So quotient rule says from where our numerator is, I'm going to go ahead and find a derivative for it. So the derivative for log base 10 of x need to be found, and then we're going to multiply that its derivative, the derivative of log base 10 of x with x squared plus 5, keeping the denominator the same without derivative, and I'm going to subtract. So similar to the product rule, but quotient rule again as a reminder, we instead of adding, we are now subtracting. Now the first term, in the next term, I'm going to keep log base 10 of x without the derivative. But then I'm going to multiply with the derivative of x squared plus 5. Okay, and so that gives us an instruction, a layout for what to do in the next step. And then the quotient rule says further that we need to divide this difference here by the square of your original denominator. So now it's x squared plus 5 being square here in our denominator. And now we are ready for getting the actual derivative. So right now it's just a layout, a foundation for our next step like that. But now let's move on. So the actual dy dx, to really get things completely taken care of, log base 10 of x. So we have learned from and recall for yourself that we have just learned earlier in this lecture that, so now we're no longer in log base e, but we're at some log with some general base. So derivative of log base a of any general base a of x is a 1 over x. But now we need to multiply with the natural log of a, where that a was the original base. Okay, and so now after that reminder, we're going to apply this understanding right here in our example problem. So now this log base 10 right here is going to give me, and of course do not blame it if the expression is starting to get a little more kind of blown up. So this is log base 10, so now our derivative directly becomes 1 over x, but multiply with a natural log of 10. But we keep that as a little fraction, and here I already had a long fraction bar getting ready to complete my entire fraction that came straight out from the quotient rule. And now this fraction there needs to be multiplied with x squared plus 5. Okay, and then we are going to subtract, and I realize that writing it this way is a little too squeezed in right here. So how about I'm going to quickly rewrite that so that we can see more space between the terms right here. Okay, so now I'm going to write it a little bit down below. So 1 over x times the natural log of 10, and then I'm going to multiply with x squared plus 5. Okay, so this came from this was the original denominator of our quotient. And then now quotient rule says we need to subtract. And now we're going to keep log base 10 of x the same. Log base 10 of x the same. And need to multiply that with the derivative of x squared plus 5, which is, quickly we apply the sum rule and the power rule here. We're looking at 2x, because the derivative of 2x becomes, derivative of x squared becomes 2x, and the derivative of 5 goes to a constant. So now we're just simply multiplying with 2x, and we're dividing all that by x squared plus 5 all squared. All right. And so as far as getting your derivative found, we're done. Okay. But so this problem here, we can spend a little time making the expression a little smaller. So watch out if your instructor is requiring you to simplify the expression, a final answer like this, then here's how we would do it. So I'm going to now move out to my next board right here. All right, so now with our current step right there, this is what we have found so far. Let me bring it back to this other board, and you can see, so this term right here is actually all one term, the little fraction 1 over x times natural log of 10 multiplied with x squared plus 5. Now we can write it first of all in one fraction. So let's do that. Okay. So it's now better to write it as x squared plus 5 over x times the natural log of 10. And then we're going to subtract the other term being log base 10 of x multiplied with 2x. Okay, and then we have an overall denominator here, x squared plus 5 all squared. Okay, so that the expression doesn't look any further simplified. Be patient at this point. Okay, so this is not, if we're looking for a simplified, this is not quite simplified yet. So But now we can make common denominator with these two terms here. So now what I see now is we can combine these two terms in the numerator as one fraction. So now I'm looking at, maybe I need to make a little more space. So I'm going to write it down below a little further. Okay, so we're looking now at x squared plus 5 minus, so I'm going to put the 2x in front of that term. It's a little easier for me to keep track that way. But now I'm going to need to multiply all that here with the extra x times natural log of 10. And then all that now is over, a x times natural log of 10. Okay, and we're putting that over x squared plus 5 squared. All right, so a little bit of algebra there again, and now you got a fraction on top of another denominator right there. Then things will all turn out to be okay. So in my next step here, allow me to erase this little part of my board. And so now, continuing from this step, then here I have to write it above here. Then x squared plus 5. Okay, and notice the 2x times and I notice I shouldn't have to have that x squared right here. So there was no square on that x, just that. So this is the step before this. So now minus 2x squared now times log base 10 of x. Okay, but now we can combine these two as one denominator. So all it is now is x times x squared plus 5 all squared and multiply with natural log of 10. But now this expression is at least one fraction. Okay, and it seems a little more simplified compared with the earlier version we have had right here. Okay, but this is a pretty direct answer right out from the box that we got the derivative done. And then in case, my point was, again, in case any instructor is asking you to simplify your final answer, and that's how you were doing that. All right. And now let's look at another example problem. And in part C of our example, what about we have y equals a sine of x plus, and now a natural log of x. Okay, so our function here has two terms. So, and the two terms here, the first term involves a trig function, and the second term is the natural log function. So now, taking a dy dx, taking the derivative here, is simply taking the derivative term by term. So my entire example 1 is just to remind you about the very basic rules, including the product rule and the quotient rule. So, and some of the special rule we've learned, say for example, the special rule for how to find the derivative of a trig function, sine of x in particular. So derivative of the first term plus the derivative of the second term. Okay. And so now derivative of the first term, sine of x, after taking the derivative, it becomes a cosine of x. And then plus, now taking the derivative of natural log of x is now going to give me 1 over x. Okay? And so as far as the straight old derivative, just getting the derivative done, we are done right here. And then in case your instructor is asking you or requiring you to combine this into one fraction, then we can make a quick little common denominator here, and your overall quotient becomes x times cosine of x plus 1 all over x. That's another way of finalizing your final answer. But these two expressions are essentially the same.